What really happens when dead stars collide? Imagine two of the universe's most extreme objects, neutron stars, on a collision course. These cosmic titans are remnants of massive stars that once burned brightly, but eventually met their end in violent supernova explosions. Now, what's left of them are incredibly dense, compact objects, each about the size of a city, but containing more mass than the sun. These stars are so dense that a single teaspoon of neutron star material would weigh around 10 million tons on Earth. And when two of these neutron stars finally collide, they unleash a spectacle that can only be described as one of the most powerful events in the cosmos. Neutron stars are born when stars many times the mass of our sun exhaust their nuclear fuel and undergo supernova explosions. If the core remnant left behind isn't massive enough to form a black hole, it collapses into a neutron star. These stars are composed almost entirely of neutrons, subatomic particles that, along with protons, make up the nuclei of atoms. But in neutron stars, the immense gravitational pressure crushes the atoms so tightly that electrons and protons combine to form neutrons. The result is a bizarre object with a density that defies comprehension. But the real magic happens when two neutron stars are locked in a binary system. Over millions of years, these two stars spiral toward each other, losing energy in the form of gravitational waves, ripples in the fabric of space-time itself. As they get closer, the gravitational waves they emit become stronger and stronger, and the stars move faster and faster, until finally they collide in a cataclysmic event. This collision releases more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. The aftermath: new stars or black holes. What happens after these stars collide is one of the biggest questions in astrophysics. When neutron stars merge, they can form a variety of different remnants depending on their combined mass and the conditions of the collision. In some cases, the remnant collapses almost immediately into a black hole, an object so dense that not even light can escape its gravitational pull. In other cases, the remnant might temporarily survive as an incredibly massive neutron star. This ultra-massive neutron star is unlike anything we've ever seen, a rapidly spinning object with extreme temperatures and magnetic fields. But this new neutron star remnant is far from stable. Scientists believe that it only has a short time before it succumbs to its own gravity and collapses into a black hole. Exactly how long this process takes is still unknown, and understanding it could unlock new insights into the physics of extreme matter. One of the most fascinating discoveries from recent research is that the remnant of a neutron star collision can be very different from its progenitors. Unlike ordinary neutron stars, which are cooler at their surface and hotter at their core, the remnants of neutron star mergers can be hotter at the surface than at the core. This temperature distribution is largely due to the fact that these remnants cool by emitting neutrinos, subatomic particles that barely interact with matter. Neutrinos carry away heat from the remnant, cooling it rapidly, forging the universe's heaviest elements. But neutron star collisions do more than just create gravitational waves and black holes. They also play a crucial role in forging the heaviest elements in the universe. When these stars collide, they eject a large amount of neutron-rich material into space. In the chaotic environment of the collision, some of this material undergoes a process known as the R process, rapid neutron capture, which creates elements heavier than iron. This is how elements like gold, platinum, and uranium are formed. These elements can't be created in the nuclear furnaces of ordinary stars. They require the extreme conditions produced by neutron star collisions. The material ejected in these collisions emits light as it decays, creating a brilliant explosion known as a kilonova. Kilonovae are much brighter than typical supernovae, and they are a key observational signature of neutron star mergers. The light from a kilonova can tell us a lot about the elements being created and the dynamics of the collision. A glimpse into dark matter? In addition to creating heavy elements, neutron star collisions might also provide a glimpse into one of the greatest mysteries in modern physics: dark matter. Dark matter is an invisible substance that makes up about 85% of the mass in the universe, but we don't yet know what it's made of. Some theories suggest that exotic particles, such as axions, could be produced in the extreme environment of a neutron star collision. If we could detect these particles, it could help us solve the dark matter puzzle. The role of magnetic fields. Another key aspect of neutron star collisions is the role of magnetic fields. Neutron stars are known for having incredibly strong magnetic fields, and when they collide, these fields can be amplified to even more extreme levels. This can lead to the formation of magnetars, neutron stars with magnetic fields 1,000 times stronger than typical neutron stars. Magnetars are some of the most powerful magnetic objects in the universe, and they emit intense bursts of gamma rays, known as gamma ray bursts, which are among the most energetic events in the cosmos. Unanswered questions. Despite the progress we've made in understanding neutron star collisions, many questions remain. For instance, what determines whether the remnant of a neutron star collision becomes a black hole or stays as a neutron star? How do the intense magnetic fields generated in these collisions influence the formation of pulsars and magnetars? And what role do neutron star collisions play in the larger story of the universe's evolution? One of the challenges in studying neutron star collisions is that they are incredibly rare. The first confirmed detection of a neutron star merger occurred in 2017, thanks to the combined efforts of gravitational wave observatories like LIGO and Virgo and telescopes around the world. Since then, only a handful of other mergers have been detected. But as our technology improves, we expect to observe many more of these events, providing new data that will help us answer these questions. The future of neutron star research. Looking ahead, scientists are excited about the potential of new observatories and instruments to study neutron star collisions. Next-generation gravitational wave detectors, like the proposed Einstein telescope and the Cosmic Explorer, will be able to detect these events from even greater distances. At the same time, space-based telescopes like the James Webb Space Telescope will allow us to observe the aftermath of neutron star collisions in unprecedented detail. These tools will enable us to study the properties of neutron stars, black holes, and the fundamental forces of nature. One area of particular interest is the study of the equation of state, EOS, of neutron star matter. The EOS describes how matter behaves at extremely high densities, and it is one of the biggest unknowns in astrophysics. By studying the gravitational waves and electromagnetic radiation emitted by neutron star collisions, scientists hope to learn more about the EOS and gain a deeper understanding of the physics of neutron stars. Another exciting possibility is the detection of continuous gravitational waves from spinning neutron stars. These waves would provide a new way to study the interiors of neutron stars and probe the nature of nuclear matter. Detecting continuous gravitational waves is extremely challenging, but with advances in technology, it may soon become a reality. Conclusion. In conclusion, neutron star collisions are some of the most powerful and mysterious events in the universe. They generate gravitational waves, create black holes, forge the heaviest elements, and offer insights into the nature of dark matter and extreme physics. These collisions are a cosmic dance of destruction and creation, reshaping our understanding of the universe and our place within it. As we continue to study these events, we are likely to uncover new secrets that will change the way we see the cosmos forever. What do you think the next big discovery will be? How might neutron star collisions reshape our understanding of the universe? Share your thoughts in the comments below. Let's explore the cosmos together.